Baltimore, Maryland, the Space Telescope Science Institute. It's 2:43 inches the morning, and the building is silent, almost reverent. A planetary scientist sits alone at her workstation, the hum of computers, the only sound in the otherwise still night. Her team left hours ago, trusting the night would pass like any other, routine and predictable. But tonight is different. Tonight, the data pipeline from the James Webb Space Telescope finished processing ahead of schedule, and what appeared on her screen demanded her full attention. What she sees is not a mere photograph. It is a three-dimensional map, an unprecedented rendering of a planetary atmosphere in depth, built from over 1,000 individual slices of spectral data. Each slice captures a different layer of Uranus's atmosphere, extending 5,000 kilometers above its cloud tops. For the first time in human history, an entire planet's atmosphere is rendered vertically, revealing the intricate structure that no Earth-based telescope could ever resolve. She begins to analyze the temperature profile. The results stop her cold. Twice she runs the data, confirming what her eyes already report. The heating peak and the ion density peak occur at entirely different altitudes, separated by thousands of kilometers. Two independent processes, operating in parallel, contradicting every model she has trusted for more than 20 years. She pulls up a 30-year cooling record, and the anomaly persists, ongoing and unresolved. Leaning back, she feels the precise, unsettling awareness of a scientist who just witnessed the collapse of a trusted theoretical framework. With careful keystrokes, she writes to her team, "We need to talk tomorrow. What the James Webb Space Telescope revealed about Uranus is not a confirmation of what we thought we knew, it is the systematic dismantling of it. To understand the full impact of this revelation, we must return to the last time humanity glimpsed Uranus up close. January 24th, 1986. NASA's Voyager 2 spacecraft completed the only close flyby of Uranus in history. Launched in 1977 to exploit a rare planetary alignment occurring once every 176 years, Voyager 2 had already rewritten what we knew about Jupiter and Saturn before it reached the seventh planet. Its encounter with Uranus was brief, a few days amid decades of distance, yet it captured precise measurements that Earth-based telescopes could not approach. At first glance, Voyager 2 appeared to confirm Uranus as a quiet, inert world. The upper atmosphere registered negative 224 degrees C, colder than Neptune despite being closer to the Sun. This anomaly alone deserved scrutiny, but the broader narrative portrayed Uranus as thermally stable, slowly radiating the meager solar energy. It received a planet seemingly in equilibrium and scientifically unremarkable. But beginning in the early 1990s, that image began to unravel. 5 years after Voyager's flyby, ground-based observatories tracking Uranus's upper atmospheric emissions began reporting a persistent cooling trend. Not random fluctuations, not seasonal oscillations, but continuous cooling over decades. This defied the models that scientists relied upon. To grasp why, we need to understand thermal equilibrium in planetary atmospheres. Every planet absorbs energy from the sun and radiates it back into space as infrared emission. A planet in equilibrium sees a balance between energy absorbed and energy emitted, resulting in a stable thermal state. Uranus, distant and receiving roughly 370 times less solar flux than Earth, should have reached equilibrium quickly on geological timescales. Its upper atmosphere should have remained consistent, yet for 30 years it cooled steadily. The implication is extraordinary. Something actively drains heat from Uranus's atmosphere faster than the sun can supply it. For decades, this mechanism remained a mystery. Uranus was distant, its emissions faint, its upper layers difficult to resolve. The cooling anomaly persisted as an unsolved cold case in planetary science. The gap in understanding was significant but unavoidable until an observatory emerged with the power to see not just the planet's surface but its vertical atmospheric layers. The James Webb Space Telescope was that observatory. Its instruments didn't just observe Uranus. They dissected it layer by layer, altitude by altitude, from cloud tops to the ionosphere, producing a dataset unlike anything before. During a nearly 15-hour uninterrupted observation covering almost a full rotation of the planet, JWST's near-infrared spectrograph or NIRSpec collected over 1,000 spectral slices. This technique, called integral field spectroscopy, generates a data cube where each spatial point contains a full spectrum. The telescope didn't just measure brightness, It measured chemical composition, temperature, particle density, and velocity across the planet's atmospheric layers simultaneously. Specifically, the focus was on H3+ ions, triatomic hydrogen molecules formed when high-energy particles ionize molecular hydrogen. These ions are particularly sensitive indicators of temperature and density, and mapping them across multiple altitudes produced something unprecedented: a fully three-dimensional structural map of Uranus's upper atmosphere. For 30 years, Uranus had presented a flat, two-dimensional facade, a blurry disk with a single temperature reading. JWST converted that facade into a volumetric dataset, revealing the hidden vertical complexity of the planet. And the results were startling. The upper atmosphere was no longer a frozen shell at -224 degrees C. At altitudes of 3,000 to 4,000 kilometers, deep in the ionosphere, temperatures reached approximately 150 degrees C. Relative to the lower layers, this represented a nearly 400 degrees temperature gradient over just a few thousand kilometers. Such a steep gradient was impossible to explain through solar heating alone. Uranus, receiving so little solar energy, required an additional, hidden source of energy, one capable of delivering heat across vast distances in the planet's upper atmosphere. But the temperature profile was only the beginning. JWST revealed that the ion density of H3+ peaked far below the thermal maximum, at around 1,000 kilometers above the clouds, creating a separation of 2,000 to 3,000 kilometers between the hottest regions and the densest ion populations. In planetary physics, this is extraordinary. On other worlds, temperature and ionization often peak together, driven by the same energy sources. Uranus, however, was orchestrating two independent mechanisms simultaneously, each operating in distinct atmospheric regions. The planet's energy budget was no longer a simple balance, but a layered, multi-mechanism system, an intricate, dynamic symphony spanning thousands of kilometers of atmospheric depth. And at the heart of this complexity was the magnetic field. Unlike Earth, whose magnetic and rotational axes align neatly, Uranus tilts 98 degrees on its side, and its magnetic axis is offset an additional 60 degrees, not passing through the planet's center. This chaotic, tumbling field drives intense heating in some regions while allowing ions to concentrate elsewhere, producing a magnetic architecture that sculpts the atmosphere itself. JWST captured this in vivid detail, revealing bright auroral bands around the predicted magnetic poles, and between them, a dark gap, a magnetic shadow, carved directly into the ionosphere. Here was visual proof of how Uranus's wild magnetism orchestrates its thermal and ion structures. Uranus was not cold and featureless. It was alive with dynamic, layered energy, a magnetically violent and thermally complex world, hiding its true nature behind an icy blue facade. And this discovery matters far beyond our solar system. Ice giants like Uranus are among the most common planets in the Milky Way, yet for decades, astronomers modeled these worlds based on a single blurry Voyager snapshot. JWST has replaced that snapshot with a forensic map, providing a physical baseline for understanding countless exoplanets. The 30-year mystery of Uranus's cooling upper atmosphere is no longer just theoretical. For the first time, we can see the engine driving it, trace its structure, and watch it operate. But the story is far from complete. To fully understand this enigmatic planet, humanity will need to go further: a dedicated probe, a direct atmospheric entry, a mission that can probe the depths JWST mapped from afar. The James Webb Space Telescope did not close the story of Uranus. It revealed that this story was only just beginning. The revelation from JWST was only the beginning. The planet that textbooks had long labeled as cold, lifeless, and unremarkable was, in reality, a dynamic system of staggering complexity. With the three-dimensional atmospheric map in hand, the research team began unraveling the mechanisms behind Uranus's puzzling energy budget. The separation of temperature and ion density peaks alone was enough to shake decades of assumptions. The H3+ ions, peaking around 1,000 kilometers above the clouds, were responding to ionization processes, primarily driven by particle precipitation from the planet's magnetosphere. The temperature peak, nearly 2,000 to 3,000 kilometers higher, required an entirely different source of energy. It could not be explained by solar heating alone, nor by a single atmospheric mechanism. The scientists considered theoretical candidates: wave heating, where acoustic or gravity waves propagate upward from the lower atmosphere; dissipating energy at higher altitudes, and Joule heating, where electrical currents induced by magnetic fields deliver energy into specific layers. Both processes could contribute, but neither had ever been directly observed at this scale in Uranus's ionosphere. JWST's data offered the first clear indication that these mechanisms were not only present, but operating simultaneously, layered like orchestral tracks, each producing a distinct atmospheric signature. The planet's thermosphere was no longer a simple, predictable system. It was a complex, interacting network of forces, each modulated by the magnetic field. And Uranus's magnetic field was unlike anything in the solar system. On Earth, our magnetic and rotational axes align neatly, producing a stable, predictable magnetosphere with auroral ovals circling the poles. Uranus, however, rolls along its orbit on its side, tilted 98 degrees from vertical, while its magnetic axis tilts an additional 60 degrees relative to its rotation and is offset from the planet's center. The resulting magnetic field does not spin cleanly. It wobbles, twists, and tumbles through space, creating a chaotic, asymmetric environment. In essence, Uranus's magnetic field is a natural laboratory for physics, a system so extreme that it challenges every model of magnetosphere-atmosphere coupling. JWST provided the first precise observational test of this chaos, revealing its effects on the planet's thermal and ion structure. The telescope's observations of Uranus's auroras offered a striking visual demonstration. Bright bands flared near the predicted magnetic poles, exactly where theoretical models suggested they would appear. Yet between these luminous regions, JWST detected a dark, depleted band, a magnetic shadow, where particle precipitation was blocked entirely. This void was not caused by the absence of atmospheric material but by the architecture of the magnetic field itself. The field dictated where energetic particles could descend, directly sculpting the ionosphere. In the bright bands, particles funneled downward, producing intense auroral emission. In the dark band, the configuration deflected particles, creating a visible gap in the upper atmosphere. This magnetic architecture also clarified the mysterious temperature mismatch. Energy input was unevenly distributed across altitudes, driven by interactions between the magnetosphere and the upper atmosphere. Some layers received intense heating from Joule dissipation and particle precipitation, while others remained comparatively cooler, creating the vertical gradient of nearly 400 degrees Celsius observed by JWST. Uranus's energy budget was not dominated by a single process. It was a multi-layered system, a dynamic interplay of physics operating across thousands of kilometers. The implications extend far beyond Uranus itself. Ice giants like Uranus and Neptune are now considered among the most common types of planets in the Milky Way. For decades, astronomers studying distant exoplanets of similar size and composition relied on models based on a single, blurry snapshot from Voyager 2 inches 1986. These models assumed relatively uniform atmospheres, simple thermal distributions, and predictable energy dynamics. JWST's map has fundamentally changed that baseline. It provides a detailed physical template for understanding how energy flows through ice giant atmospheres, how magnetic fields sculpt ionospheric structure, and how multiple processes interact to drive temperature and ion density distributions. In short, the telescope has redefined what we know about billions of planets across our galaxy. But the discoveries go even deeper. Uranus's unique magnetic geometry challenges conventional understanding of planetary dynamics. The off-center, tilted, and tumbling magnetic field creates asymmetries that produce not only the visible magnetic shadow, but also intricate patterns of energy transport. The observations suggest that magnetic topology, rotation, and particle interactions combine to orchestrate a complex atmospheric symphony. This is physics made visible, a system where the rules of energy transfer are written not just in equations, but in the very structure of the planet. The planet is a laboratory, and JWST has given scientists the instruments to read the score. The three-dimensional map also offers insight into the long-standing cooling mystery. Uranus's upper atmosphere has been losing heat continuously for decades, an anomaly that defied all theoretical predictions. JWST shows that the heat is not simply vanishing, it is being redistributed and transformed through interactions between the atmosphere and the chaotic magnetosphere. Energy injected in some layers and blocked in others creates the observed cooling pattern, a dynamic equilibrium invisible to previous instruments. This is the first time that the engine behind Uranus's thermal behavior has been traced, layer by layer, altitude by altitude. Scientists can now see how heating, cooling, and ionization interweave to produce the complex state of the upper atmosphere. This complexity explains why Uranus appeared so featureless in earlier observations. From a distance, the planet's blue-green exterior hides its dynamic interior. Its clouds are deceptive, presenting a calm facade that belies the storm of physical processes occurring above. JWST has peeled back this veil, revealing a planet that is anything but inactive. Its atmosphere is structured, layered, magnetically sculpted, and thermally dynamic. The old assumptions of a cold, dead ice giant have been shattered. Yet the story is far from complete. JWST can map the upper atmosphere and ionosphere, but it cannot probe the depths directly. To fully understand Uranus, scientists must plan a dedicated mission, an atmospheric entry probe capable of sampling the planet's interior, measuring energy flows directly, and tracing the interactions between magnetosphere and atmosphere in situ. JWST has set the stage, transforming Uranus from a distant curiosity into a target for the next generation of planetary exploration. The telescope did not close the chapter on Uranus. It opened a new one. Every layer of data, every temperature gradient, every magnetic anomaly tells a story of complexity and energy we are only beginning to understand. The planet that once seemed a frozen, static world is now revealed as a dynamic, multi-layered system, a natural laboratory for understanding the behavior of ice giants, both in our solar system and beyond. The mysteries unveiled by JWST are a reminder that even the planets we think we know best can surprise us, challenging decades of assumptions and forcing us to rethink the fundamental physics of planetary atmospheres. With the James Webb Space Telescope's three-dimensional map, Uranus has emerged from decades of obscurity to become one of the most studied and most mysterious planets in the solar system. What was once dismissed as a static, icy world is now understood as a multi-layered system of complex atmospheric, thermal, and magnetic interactions. The vertical separation of temperature and ion density peaks, the chaotic magnetic field, and the auroral patterns all tell a story of a planet operating on multiple energy layers, a system far more intricate than any prior model could predict. But beyond the immediate revelations about Uranus itself, these findings have profound implications for planetary science as a whole. Ice giants are among the most common planets in our galaxy, and for years, astronomers modeled them based on assumptions drawn from a single blurry Voyager snapshot from 1986. Every exoplanet of similar size, mass, or composition was interpreted with this limited perspective. Now, JWST has provided a detailed physical template, a forensic map of how energy moves through an ice giant's atmosphere, how magnetism structures the ionosphere, and how thermal and ion processes interweave across thousands of kilometers of vertical space. This template is no longer an approximation. It is a detailed, three-dimensional reference that will redefine how we interpret ice giant exoplanets across the Milky Way. Consider the broader consequences. Exoplanets that were previously modeled as cold, featureless, or static may in reality host complex, layered atmospheres shaped by magnetic fields, particle precipitation, and intricate heating mechanisms. The energy budgets of these worlds, their potential for auroras, and even the transport of chemical species may mirror the multi-layered processes observed in Uranus. In other words, what JWST revealed about a single planet in our solar system could change the way we study billions of planets orbiting distant stars. Every model of atmospheric circulation, every prediction of thermal behavior, every estimate of habitability for ice giants now needs to account for the lessons learned from Uranus. But the mystery is not fully solved. JWST mapped the upper atmosphere and ionosphere, but it cannot directly sample the planet's interior. The observed thermal anomalies and magnetic phenomena hint at processes operating deep within the planet, beneath layers we cannot yet access. To fully understand the engine driving Uranus's atmosphere, scientists will need a dedicated atmospheric entry probe capable of measuring temperature, pressure, particle flux, and magnetic fields directly within the planet itself. Only through such a mission can we connect the dots between surface observations, magnetospheric architecture, and deep atmospheric dynamics. Until that day, JWST has given us the blueprint, a starting point for a new era of planetary exploration. The data also highlights the incredible synergy between modern observational technology and theoretical physics. Uranus, with its extreme tilt, off-center magnetic field, and multi-layered energy processes, is a natural laboratory for testing theories that were previously only abstract. It challenges our understanding of how magnetic fields couple with planetary atmospheres, how energy propagates through complex systems, and how atmospheric structures evolve over time. Observing these phenomena in situ, or at least in unprecedented three-dimensional detail, provides validation for models that can then be applied to worlds far beyond our solar system. In essence, Uranus is a Rosetta Stone for ice giants, translating decades of theoretical physics into observable phenomena. And yet, the story is far from complete. Each discovery opens new questions. How does Uranus sustain heating in the ionosphere at altitudes far above the cloud tops? What role do gravity waves, Joule heating, and particle precipitation play in the planet's long-term energy balance? How do the chaotic magnetic geometry and extreme axial tilt interact to create the layered, non-uniform temperature distribution? JWST has given us answers, but it has also revealed the profound complexity of planetary systems we thought we understood. The planet that seemed quiet and uneventful is a dynamic, living laboratory for physics, one that will keep scientists busy for decades to come. Beyond the immediate scientific community, these revelations hold significance for the broader public imagination. Uranus has long been treated as a footnote in planetary science, a distant blue-green dot with few interesting features. JWST's observations transform it into a dynamic, almost theatrical presence in the solar system, a planet whose magnetic storms, temperature gradients, and auroral bands can now be visualized in stunning three-dimensional detail. It is a testament to human curiosity and ingenuity that a machine 1.5 million kilometers from Earth can render these distant phenomena, allowing us to witness a world's energy and magnetism from across the solar system. The mission of JWST to Uranus is also a reminder of how much there still is to discover. Even in our own cosmic backyard, we are uncovering mysteries that challenge decades of assumptions. The story of Uranus exemplifies the evolving nature of scientific understanding. What was once considered settled knowledge can be upended by new technology, persistence, and careful observation. It is a lesson not only in planetary science but in the broader practice of inquiry itself, demonstrating that the universe is far more complex, layered, and interconnected than our models can fully capture. Looking forward, Uranus sets a precedent. Ice giants are now understood to be dynamic, structured, and magnetically intricate. Future missions, whether atmospheric probes, orbital satellites, or even remote JWST observations, will build on this foundation. JWST has not finished the story, but it has provided the roadmap. Scientists now know what questions to ask, what instruments to build, and which measurements will yield the most insight. Each subsequent observation will refine our understanding of ice giants, guiding humanity toward a more complete picture of these common but enigmatic planets. For those fascinated by the cosmos, the tale of Uranus reminds us that even the planets we assume we know best can surprise us. The cold, blue-green giant that once seemed featureless now reveals a complex symphony of energy, magnetism, and chemistry layered and interacting in ways we are only beginning to grasp. It challenges our understanding, redefines our models, and opens the door to insights that extend far beyond our solar system. Uranus is no longer a footnote. It is a teacher, a laboratory, and a source of inspiration for planetary science and exploration. As the James Webb Space Telescope continues its mission, we can expect more revelations that challenge the boundaries of our knowledge. Uranus is just one planet, but it has already rewritten decades of assumptions and illuminated the path for understanding ice giants across the galaxy. The story of Uranus is a story of patience, innovation, and the relentless pursuit of knowledge, a story that shows us that even in the seemingly quiet corners of the solar system, the universe is alive with mysteries waiting to be uncovered. If you want to stay updated on these groundbreaking discoveries and explore the mysteries of our solar system in detail, make sure to hit that subscribe button, turn on notifications, and join us on this journey to uncover the hidden workings of the cosmos. The story of Uranus is only the beginning, and you won't want to miss what comes next.